All right, today we're basically detectives. We've got a mystery on our hands, an unknown piece of metal. And our only clue? How it behaves when we mess with its temperature. Our mission is to figure out its secret identity just by measuring one of its most basic properties.
So how in the world can you take a simple temperature reading and turn that into a positive ID for a piece of metal? Well, that's exactly what we're about to break down. Let's get into it.
Here's our game plan. We'll kick things off with the mission. Then we'll get a really solid understanding of the science behind it, specific heat. After that, we'll check out the equipment you'll be using. I'll walk you through the procedures step by step. And finally, we'll crunch the numbers to solve the case.
So, your mission, should you choose to accept it, is to step into the shoes of a material scientist for the day. We're going to use a technique called calorimetry to get a super accurate measurement of a unique physical property of this metal. And that property is going to lead us straight to its identity.
Now, to crack this case, you've got to understand the main tool in our toolbox, the concept of specific heat. This is the scientific principle that makes this whole thing possible.
So what is it? Well, specific heat is just the amount of energy you need to raise 1 gram of something by 1 single degree Celsius. We measure it in calories, or, like we'll be doing today, in joules. The best way to think about it is like a chemical fingerprint. Every single substance has its own unique value. And hey, don't get this confused with heat capacity. Heat capacity is about the whole object, no matter its size. Specific heat is what we care about. It's that unique per gram fingerprint we're hunting for.
And this right here, this is our book of fingerprints. This table has all the known specific heat values for a bunch of different substances. Once we finish our experiment and calculate the value for our mystery metal, we're going to come right back to this chart and find the match. This is our answer key. Hey, take a close look at the value for water. See that? 4.18. It is way higher than any of the metals on the list. This means water is like an incredible heat sponge. It can soak up a ton of energy without its temperature shooting up like crazy. And that unique property, that's our secret weapon for this experiment.
All right, enough theory, let's get practical. It's time to meet the tools of the trade you'll be using to conduct this whole investigation.
So here's your setup. You've got a thermometer for your temperature readings, a microwave or stove to heat up the water, a graduated cylinder and a scale for getting those precise measurements, and of course, our mystery metals. Oh, and that plain old Styrofoam cup, believe it or not, that's our star player.
Yep, you heard me. That simple coffee cup is our calorimeter. Its whole job is to be an insulated container that traps heat. And Styrofoam is perfect for this because it's full of tiny pockets of air, and air is a terrible conductor of heat. This setup helps make sure the heat transfer we're measuring is happening between the metal and the water, not just escaping out into the room. Pro tip, if you want to make it even better, you can wrap the outside with some aluminum foil.
And now for the main event, the actual procedure. I know it might look like a lot of steps on paper, but we can break it all down into a few really simple phases. So let's walk through it together. When you really boil it down, it's just 5 main things. You get your metal ready, you put your calorimeter together, you prep the water, you combine everything, and then you record that final temperature. Simple as that. Now let's zoom in on a couple of key details that are absolutely critical for getting a good result.
Okay, this first part is super important, so listen up. After you get the mass of your metal, you need to stick it in the freezer and leave it there overnight. This is crucial because it gives us a known cold starting temperature. We're going to assume that temperature is negative 18 degrees Celsius, which is pretty standard for a home freezer. And then, when you get to the very end, this is where patience really pays off. After you drop that frozen metal into your warm water and put the lid on, you're going to want to swirl it gently and then just wait. You have to give the system a minute or two to reach what we call thermal equilibrium. That's just the point where the metal and the water stop changing and become the exact same temperature. That final, stable number is the one you need to write down. So, you've done the prep, you've run the experiment, and you've got all your data written down. Now it's time for the fun part. At least, I think it's fun. It's time to do the math and finally reveal this metal's identity. The entire calculation, the whole thing, hinges on one simple, beautiful law of physics. The heat that the cold metal gains has to come from somewhere, right? And inside our insulated cup, that somewhere is the warm water. So the heat lost by the water is equal to the heat gained by the metal. It's a perfect trade. First things first, we've got to calculate how much heat the water actually lost. We use this formula right here. You take the mass of the water, multiply it by the change in its temperature, and then multiply that by the specific heat of water, which we know is 4.18. This will tell us exactly how many joules of energy got transferred.
Now, using the example data from the lab handout, let's say you had 100 grams of water and it cooled down by 5.2 degrees. Well, the math shows that the water gave away exactly 2,173.6 joules of energy. Remember that number, it's important.
Now we get to solve for our unknown. Because the heat gained by the metal is the same as the heat lost by the water, we can take that exact same energy value, that 2,173.6 joules, and just plug it right into the specific heat formula for our metal. All we're doing is rearranging the formula a bit to solve for the specific heat itself.
And here is where it all comes together beautifully. You take that heat value, you divide it by the metal's mass, times its change in temperature, and boom, out pops your answer. In this example calculation, the specific heat comes out to 0.999 joules per gram degree Celsius. So, what do we do with that number? We go right back to our table of fingerprints. Our result of 0.999 is really close to aluminum's known value of 0.903. Now, you might be thinking, hey, that's not a perfect match. And you're right, but in a real-world experiment like this one, you're always going to lose a little bit of heat to the air or to the cup itself. Factoring in that little bit of experimental error, our evidence is pointing overwhelmingly to one conclusion: the mystery metal is aluminum. Case closed.
So let's do a quick mission debrief. We learned that specific heat is basically a substance's unique fingerprint. We saw how to use a simple styrofoam cup as a calorimeter to measure temperature changes when heat gets exchanged. We calculated that heat transfer and used it to find the specific heat of our unknown metal. And then we compared that result to a chart of known values to make our final ID.
You've got the background, you know the procedure, and you know how to do the math. You are officially ready to play detective. Your metal is waiting for you in the freezer. The only question left is, what will its secret identity be?